Okay, so let us start from where we left off in the previous video. In fact, let's just see one thing that we have already seen before. From there we start, namely x separating a and b. Let this be our graph. If a and b are sets of vertices and x is a subset of V union E, so that x may have vertices as well as edges, and these things are such that every AB path contains a vertex or an edge from X. Then we say that X separates A and B in the graph G. Now we have already seen one small example in the previous video illustrating this point, so we are not going to do that again. And there we have also seen this fact. This implies means if X separates A and B, then A intersection B is contained in X. Because if you take one vertex in A intersection B, then that vertex itself will form an AB path. So according to the condition that X separates A and B, that path should contain something from X. Since the path has only one thing, namely that vertex, so that vertex should belong to X, and that's how A intersection B should be contained in X. More generally, we say that X separates the graph G if G minus X is disconnected. We know how to find G minus X. The vertices that X has, those, when we remove those vertices, we also remove the edges incident with those vertices. And when we remove the edges in X, if X has any edge, then we just remove them from the graph. So if G minus X is disconnected, then we say that X separates the graph G itself. That is, if X separates in G some two vertices that are not in X, of course, because after the removal there should be, I mean, whatever we are separating, they should be there present after the removal of X. Okay. A separating set of vertices is called a separator. If it see, X is allowed to have both vertices and edges. It can have anything. Now if it happens that X has only vertices and X separates some sets A and B, or in general X separates G, then we call such a set X a separator. So when you say something is a separator, then it is separating a graph and it has only vertices. Separating sets of edges have no generic name. So we don't call them some by, I mean, we haven't given them some special name like separator if such a set X has only edges. However, in some special cases they do have names, but some such sets do. And in this regard, one can see section 1 by, is it the 9th one? Yes. For the definitions of cuts and bonds. Now if it happens that X is singleton, then of course there are some names. A vertex that separates a vertex that separates two other vertices. Do you know what I was looking over there? I forgot the spelling of the word separates. For a moment it felt like we should have an E here instead of A. So that's what I tried to make sure. Anyway, a vertex that separates two other vertices in the same component is called a cut vertex. So if our X has only one vertex, then if it separates two other vertices in the same component, then such a vertex is called a cut vertex. And in this case, we don't view that vertex as a set, but just simply as a vertex. Is called a cut vertex. And similarly, if we have a single edge that is separating a graph, that separates its ends is called a bridge. Instead of writing like this, one could have written just in terms of this x also. If x has a single vertex, then that vertex is called a cut vertex, because if x is a separator, that is a separating set of vertices in a graph, then obviously removal of x will separate some things. So it will separate some two other vertices in the same component, of course. And if x has a single edge, then if removing that edge separates the graph, then whatever happens, the two ends of the edge must always be separated. They should, after the removal of the edge, they should lie in different components. So such an edge is called a bridge. If you burn the bridge, then that's it. The two ends are disconnected. So bridges in a graph are precisely those edges that do not lie on any cycle. That is because if your edge is lying on a cycle, then its removal will not make any graph disconnected, unless of course the graph has only but if it belongs to a cycle, then it cannot have only two vertices. It should have more than two vertices. So what we have said here in the last line is this: if there is a cycle in a graph, then removal of any edge of this cycle does not separate anything. The two ends are still connected by this path. So that means bridges are precisely those edges that do not lie on any cycle. For example, if I make this one an edge, if we have this graph, say, in this graph, none of these edges is a bridge. However, this edge is a bridge. Its removal separates these two ends. Now to illustrate this notions of cut vertex and bridge, there is one example given in the text. that I will now draw. In fact, no one will bother to draw these things using rulers, because it does not really matter how you draw the edges. The edges can be carved, not necessarily straight lines, and they can be drawn in any manner. But it looks good. So just for the sake of looking good, I am using the ruler. And there is another part of this graph which is in a separate component. In the text, that component is drawn alongside this one, but I don't have space, and it does not matter also. We can draw the other component in any manner we want, as long as we draw it. So we can draw it below this one. So this is the entire graph, and in this graph some vertices have been given names. V, X, Y, and this edge is E, and this one is W. The description of the graph is this: a graph with cut vertices V, X, Y, W and bridge E, whose ends are X and Y. So you can clearly see that this is a cut vertex. Its removal, for example, will separate this vertex and this vertex. Or you can think of it in this way also. Removal of V increases the number of components. After removing V, the original graph before removing V has 2 components. After removing V, it will have 3 components. So similarly, removal of X or Y or W will increase the number of components. So these are all cut vertices, and if we remove the edge E, then also the number of components increases, and its ends, which are X and Y, they are separated. Note that none of the other vertices in this graph is a cut vertex. For example, if you remove this one, then the number of components does not increase. Similarly, if you remove the upper or lower vertices, then the number of components does not increase. Similarly, for these 4 vertices, and because of this last line, the only bridge in this graph is this one, which does not lie on any cycle, which is not a part of a cycle. You see that all the other edges are parts of some cycles. Here in this component there is one cut vertex and no bridge. In this component there are 3 cut vertices and 1 bridge. Okay. Now after this there is something else. The unordered pair A comma B is called a separation of G if union of A and B equals the vertex set phi and there is no edge. And there is no edge between A minus B and B minus A. Okay, so if you are we look at this sentence, first of all we don't see what A and B actually are, but in this condition we can see that A and B are sets of vertices, so that their union is the entire vertex set of the graph, and additionally there is no edge between A minus B and B minus A. If this happens, then we say that this unordered pair is a separation of G. Clearly, this last condition is equivalent to the statement that A intersection B separates A and B in G. But how? Let us see. Last condition means the condition which says that there is no edge between A minus B and B minus A. The more we see this type of notions, the less examples I will provide. Okay, that is because you should be able to come up with some examples for your own, on your own and for yourself, that illustrates this. For example, a separation. So you take a graph and there you identify two sets A and B, such that these conditions are satisfied, then such an ordered pair will be a separation for that graph. Note that in this definition of separation, we are not saying that A and B are disjoint. In fact, A and B may have something in common, some common vertex. So we are not saying in particular that A and B form a partition of the vertex set. That is not the case necessarily. Now, how are we saying that this condition is equivalent to the statement that A intersection B separates A and B in G? Let us see roughly. So suppose this is our A and this is our B. These are not Venn diagrams, okay? So these lobes or these regions don't suggest that A and B are disjoint. So first assume that this is a separation of G. Suppose now you want to show that A intersection B separates A and B. That means every AB path in G should contain at least some vertex from A intersection B. Suppose that is not the case, then there exists an AB path joining a vertex from A to a vertex from B that does not have anything from A intersection B. None of the vertices in this path belongs to both A and B. Okay. Then what? This vertex of course belongs to A and this vertex belongs to B. That is because this is taken to be an AB path. Now look at this condition. A union B is V. So all the other intermediate vertices, if there is any, each one of them should either belong to A or it should belong to B. But according to our supposition, none of such intermediate vertices belongs to both A and B because they are not, none of them is contained in A intersection B. So that means we can classify them into two parts depending on whether it belongs to A or it belongs to B. And in that classification you will see, in fact you can see, you can imagine the situation that you will come across two vertices that are adjacent in this path such that one belongs to A and the other belongs to B, no matter how the path goes from A to B. Remember that although I am showing the path in a simple manner like this, it may happen that part of the path goes from a point or in A to a point in B and then again comes back. Like that it does several times and then finally it lands at some vertex in B. That may be the case, but the thing is that whatever the situation may be, we will always come across one edge, one of whose ends belongs to A and the other end belongs to B. Okay, now according to our supposition, since none of the vertices belongs to A intersection B, so the end that belongs to A, it belongs to A only, and the end that belongs to B, that belongs to B only. So that means this belongs to A minus B and this end belongs to B minus A. But then you have an edge between A minus B and B minus A, which contradicts this condition. So our supposition that this path has no vertex that is coming from A intersection B is wrong. There must be something that is coming from A intersection B, and that's why A intersection B separates A and B in G. Now if you want to look at the converse, suppose you again have A and B, and this time our assumption is that A intersection B separates A and B in G. So any AB path has something from A intersection B. We want to prove that there is no edge between A minus B and B minus A. Now suppose that is not true, that there is an edge whose one end belongs to A minus B and the other end belongs to B minus A. Okay, in the previous, okay, let us just first see this one. I think what I said here is not entirely correct. Let's first handle this one and then we will go back to this. Then, so now what is our assumption? Our hypothesis is that A intersection B separates A and B in G, and we are supposed to show that there is no path, no edge between A minus B and B minus A. To the contrary, we have supposed that there is one such edge. Then this itself is an AB path. Why? Because one end belongs to A and the other end belongs to B. So this AB path should contain, according to our hypothesis, something from A intersection B. But that something should either be this one or this one, which is not possible because this one belongs to A only and this one belongs to B only. So our supposition that there is one such edge is wrong, and hence there can be no edge between A minus B and B minus A. Okay. Now what I was saying, we have got a little wrong about this previous argument is this. Remember, this is any AB path. So one end belongs to A. Okay. So the part of the argument where I said that the path can go like this and then again come back and do like that several times, then ultimately lands at some vertex in B is wrong actually. Why? Because by the definition of an AB path, an AB path should be like this. Suppose this is your set A, this is your set B. The AB path joins a vertex from A to a vertex from B in such a way that the intermediate vertices belong to neither A nor B. Okay, that is the definition of an AB path. So the way we have taken an AB path here, it will never come back. That is because if it comes back, then this intermediate vertex belongs to B, and that violates the definition of an AB path. And in fact, you can see that the fact that this is an AB path implies, if you combine that with this condition, it implies that in the path actually there can be only two vertices. That is because according to the definition of an AB path, the intermediate vertices should neither belong to A nor belong to B. but A and B are all we have. We don't have anything outside both A and B, so there can be no intermediate vertices, and that's why this AB path should only be a single edge. So in that part of the argument, actually our argument is simplified. We don't have to consider such complexities like this. They don't occur at all. Okay, so now you can see that if this is a separation of G, then A intersection B should separate A and B in G, and the converse is also true. When we are arguing like this about graphs, it is very easy to make mistakes. That's because when we are saying something general like that, we are often saying a statement or something about infinitely many graphs at once. For example, in a graph, A and B form a separation. The graph itself can be of any type. The only thing that is common to all such graphs about which we are saying, giving this general argument, is that A and B, when taken together, they give you all the vertices, and there is no edge between A minus B and B minus A. Other than these two things, there can be many different types of graphs, and you can almost imagine there are infinitely many such graphs. And in a single graph itself, there may be many such unordered pairs. So you should be very careful when going through some argument in graph theory. Anyway, so now moving on with this. The separation is called proper if both A minus B and B minus A are non-empty. The number of elements in A intersection B is called the order of the separation. Okay. Now next we go to the definition of connectedness. K-connectedness. A graph G is said to be K-connected, K-connected, where K is a natural number. That means K is a non-negative integer if our graph has more than k vertices and g minus x is connected for all subsets x of v satisfying this. So a graph is said to be k connected where k is a non-negative integer if the graph has more than k vertices and removal of any set of vertices from the graph that has less than k vertices does not disconnect the graph. It keeps the graph connected. If this happens, then we say that the graph is k connected. It may be somewhat difficult to see what the definition means in the beginning when one looks at it for the first time. Let us just go through it, and then of course we will see the illustrating example and things then will be much more clear. So any, okay, I should have written any non-empty graph is zero connected and one connected graphs are precisely one connected graphs are precisely the non-trivial disconnected graphs. Non-trivial, no, not disconnected graphs, non-trivial connected graphs. What is all this? Let's see. Let us first, without really going very deep into the definition, try to verify these things just mechanically. We are saying that any non-empty graph is zero connected. So that means we should have 0 in place of k. So a zero connected graph G should satisfy these things, and G minus X is connected for all x satisfying this. Okay. Now this condition tells us that G should have order greater than 0. That means the graph should have at least one vertex. So that's why non-empty. And what about this second condition? This second condition can also be written in another manner as an implication. X is a subset of V, subset of the vertex set of the graph, and X has less than 0 elements, less than 0 vertices implies G minus X is connected. This implication is vacuously true. Because the hypothesis of this implication is a conjunction and one part of that is false. No set X is there whose cardinality, which in this case of course is the number of elements because we are dealing with finite sets, is less than 0. Cardinality by definition is always greater than or equal to 0. It's a at least for finite sets, it's a non-negative integer. So this part is false, so that means the implication is vacuously true, but true nonetheless. So any non-empty graph is automatically 0 connected. And then we are saying the one connected graphs are precisely the non-trivial connected graphs. How? Let us take a non-trivial connected graph. Say G is a non-trivial connected graph. Non-trivial means it has either more than one vertex or no, non-trivial means it should have more than one vertex. So that means we should have this, because the two trivial cases are, one of them the empty graph and the other one is the graph consisting of a single vertex. So this is a non-trivial graph and the graph is connected. So if we consider this condition itself, in this case, in this particular case, with 0 replaced by 1, then we have this. Is it true? Let us see. This tells us what? That cardinality of x should be equal to 0. That is, x should be empty. So that is the only possibility for, that is the only choice for x. What about the conclusion of the implication? This must be connected, which is nothing but G itself, and G is given to be connected, so that's why this condition is true, and this of course is true because we have chosen G to be non-trivial. So any non-trivial connected graph is one connected. Conversely, if you have a one connected graph, then from the definition of one connectedness, this must be true and this must be true. this must be true means what? That this part of the implication, that is the hypothesis of the implication, again gives us that X must be empty. But now the conclusion is not given to us. The conclusion is coming from the fact that we have assumed G to be one connected. So that's why this must imply this. So that means G minus empty set should be connected, which is G itself. So that's why G should be connected. And that is why the one connected graphs are precisely all the non-trivial connected graphs. And besides all these things, we also have the actual, there is one quantity called vertex connectivity or simply connectivity. That is the next thing. The greatest integer such that it's taking forever to clean the board. No? I will do something about it tomorrow. It is happening because of the increased humidity. It's been cloudy, and because of this ink also, I need to change the ink. It's too sticky. The greatest integer k such that a graph G is k connected is called the connectivity, vertex connectivity, but we don't mention the word vertex. There is another notion, namely edge connectivity. Kappa of G. This is the Greek letter kappa of G. Okay, so we are saying that if a graph is k connected for some non-negative integer k and not k plus 1 connected, then we say that the connectivity of the graph kappa of G is k. Thus, this is written almost like k, the letter k itself. This is equal to 0 if and only if and only if G is disconnected or K1, that is the graph having only one vertex. Now what are we saying here? kappa of g equal to 0 means what? It means that G is a zero connected graph but not one connected graph. Zero connected graphs are any non-trivial graph is zero connected. Okay, and we are given an if and only if statement here. So let's try to understand this, understand both the sides. First, assume that kappa of G is equal to 0. That means G is zero connected. So G is a non-trivial graph. Fine. G has more than one vertex. So these conditions are true. And at the same time, G is not one connected. Now, any non-trivial connected graph is one connected. So that means G is not one connected means G is either not non-trivial or not connected. If G is not non-trivial means G is trivial. However, among the two possibilities of the trivial graph, one of them is the empty graph and the other one is K1. This is not possible because G has at least one vertex. So in that case, G must be equal to K1. And if G is not connected, then G is disconnected. So we see that if this is the case, then G is either disconnected or K1. Conversely, if G is K1 or disconnected, okay, if G is K1 or disconnected, then what? Can G be the empty graph? Definitely not, because if G is K1, then it's not empty. If G is disconnected, then it should have at least two vertices which are not linked by any path in G. So that means the empty graph is ruled out. Okay, so which means what? That G should have at least one vertex. So that means this is true. And we have already seen that any non-empty graph is zero connected. So that means our G is zero connected. And now we need to argue that G is not one connected. So the one connected graphs are non-trivial connected graphs. If G is K1, then it cannot be one connected because it does not have more than one vertex. So that case is settled. If G is disconnected, then it has more than one vertex. However, it is not connected, so it cannot be a one connected graph. So that's why a graph that satisfies these two things, that is, it is either disconnected or K1, is zero connected and not one connected. So that's why 0 is the largest integer k such that G is k connected. So kappa of G is equal to 0. And we have put a comma here, that is because there is another statement, kappa of the complete graph kn on n vertices is n minus 1. Now how is this one coming? Note that to prove this one, we need to just show that kn is n minus 1 connected. Is kn n minus 1 connected? Let's see. What is the number of vertices in kn? N. So this is greater than n minus 1. So the first condition for n minus 1 connectedness is true. Now if we remove a set of vertices from Kn whose cardinality is less than n minus 1, is this connected? Yes, it is, because in Kn any two distinct vertices are adjacent. So unless you remove all the edges, you cannot have a disconnected graph. And we are not removing edges, we are removing vertices. So the maximum size of X can be n minus 2, in which case also this is connected. So Kn is n minus 1 connected. Now then you say, how does that in itself imply that the connectivity is n minus 1? That is because no higher connectivity is meaningful. You see, Kn has only n vertices. So the maximum value of K that we can have here in the definition of K connectedness for the graph Kn is n minus 1, because K has to be less than the number of vertices in the graph. So that's why n minus 1 is automatically the largest K for which Kn is K connected, and that is why the connectivity is n minus 1. Now all these things may seem like too much, and it may seem like the definition is extremely difficult to apply, and it's quite, it takes quite a lot to just decide whether a graph is K connected, let alone decide its connectivity. But actually, we will now try to simplify the definition. If we, without understanding anything, see the arguments that we have gone through right now, we have done so mechanically without understanding anything. We just saw whether the conditions are true or not for a given graph, and as if we are some computing machine, we concluded that yes, this is the case, that Kn has connectivity n minus 1 and so on. But the definition is not that difficult, truly. You see, what the definition says is this: the number of vertices should be greater than K, and when you are removing a set of vertices from G whose cardinality is less than K, then this remains connected. Okay, so then we are saying that G is K connected, and the largest such K is the connectivity of G. So it just says what? It says that if a graph has connectivity K, so connectivity itself is K, then removal of any number of vertices from the graph less than K will keep it connected. However, there will be a set of some K vertices in the graph whose removal will give you a disconnected graph. That means if you are, it's like what possible analogy I can give. It's like there is a very bad and evil monarch in a country who is ruling very badly, cruelly, mistreating people. Now, people want to eliminate the monarch. Then they gather other people, other vertices. The monarch's strength is K, in the sense that if you gather K people to I should not say like that. If you gather less than K people and then try to revolt against the monarch, then you will not be successful. The monarchy will not get eliminated. Okay, so the graph stays disconnected, but there are some special K number of people, not all any arbitrarily chosen K people, but some special K number of people. If you gather those special strong people together, then the thing can be changed. Then you can make the graph disconnected. For example, now this is not how the example is given in the text. However, it seems better to present the example now itself. You look at this graph. This is a graph G whose connectivity is 4. You can see in this graph, if you remove any 3 vertices, the resulting subgraph stays disconnected. Connected. What the hell am I saying? Stays connected. For example, there are many choices, of course, for a set of 3 vertices. If you try to remove these 3, then you are left with a triangle. Same if you remove these 3, these outer vertices. If you remove any of these 3 vertices, then also you are left with a triangle. You can see, and after some time you will get convinced that removal of 3 vertices is not enough to disconnect the graph. But there are 4 vertices whose removal will disconnect the graph. And these are if you remove these 4 vertices, there are others of course, other sets of 4 vertices are there, then that set consisting of these 4 vertices separates the graph because these 2 vertices are separated. Note that if you remove any 4 vertices, then there is no guarantee that the graph will get separated. For example, if you remove this one, this one, this one and this one, then you are left with K2, which is connected, but these special 4 vertices, or there are others like that, are there is at least one set X whose cardinality is 4, such that removal of X makes the graph disconnected. So that's why its connectivity is 4. That is the minimum that has to be removed to make the graph disconnected. That is the notion of connectivity. And just like this, there is another edge connectivity. If G has more than one vertex and G minus F is connected for any subset F of E, the set of edges satisfying this, then we say that G is like there we had K connected, in this case L edge connected. The greatest integer L for which G is LH connected is called the edge connectivity of G, just like that simple connectivity or vertex connectivity. And there also the definition of edge connectivity has a similar interpretation. The greatest integer L such that G is LH connected is called this is not T, okay, this is L hyphen. The edge connectivity, and that is denoted by lambda of G of G. We have in particular we have lambda of g equal to 0 if g is disconnected. Okay, now to illustrate these notions, there are two examples given. One of them is this. Now, in this case, the vertex connectivity is 4 and the edge connectivity is also 4. Need some quick ink. Okay, why is edge connectivity 4? Edge connectivity also has a similar interpretation. Edge connectivity 4 means if you remove 3 or any 3 or fewer edges, the graph will stay connected. But there are 4 special edges, at least a set of 4 edges whose removal makes the graph disconnected. You can see if you remove any 3 edges, the graph stays connected. That I leave to you. But if you remove these 4 edges, for example, this one, this one, this one, and this one, then the lower vertices are separated from this one, the top one. So it becomes disconnected. So edge connectivity is 4. And there is another graph where the vertex and edge connectivity are different. So that one is this. Okay. There is no edge between these two. Okay, fine, but there are 2 other vertices which are first of all they are adjacent, and then these 2 are adjacent, these 2 are adjacent, and these 2 are also adjacent. Okay, similarly here. you will realize that when you start drawing bigger and bigger graphs, there is an advantage of edges drawn or shown by straight lines. The advantage is that you can see that the things have already become quite complicated and the edges seem to have cluttered the space, although there are only a few vertices. So when you can draw curved edges in whatever manner you can, but the thing is that if your edges are straight, you can quickly see which vertices are adjacent much more easily from the diagram. Although there are many edges, but we can quickly see that this has 1, 2, 3, 4, 5, 6, 7 neighbors. So such things can be quickly decided if the edges are drawn straight. For this graph A, let us call it H. The connectivity kappa is still the connectivity here decreases, but the H connectivity remains the same. Connectivity decreases means there are some two vertices in the graph whose removal disconnects the graph. You can see that these are two such vertices. If you remove them, this part and this part, they are separated. So connectivity is 2, and removal of just a single vertex does not disconnect the graph. However, edge connectivity still remains 4. You have to remove 4 edges to make the graph disconnected. But which 4 edges? These 4 edges, removal of these edges will separate this vertex from the rest of the graph, from the other vertices, or increases the number of components. So I said that I will try to complete this section in this video itself, but I think that will be unwise, and let us first let these things sink in for some time, and then we will go to, because after this we have a proposition which says that if G is a non-trivial graph, then its connectivity is less than or equal to its H connectivity, which is less than or equal to the minimum degree. And the proof has some subtleties. We have to go through them carefully, so we cannot rush through the things. So I think it's better to stop this video here itself. I am also going slowly and carefully so that I don't make any mistake. So that will be all in graph theory in this video. Tomorrow again, last week we did fields. So that means tomorrow again vector spaces and modules. Modules, of course, we have some time before anything from that part comes. So anyway, let me wrap up. So see you in the next video. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.